Yeah, it's a little bit annoying, but yeah, this is a free lunch, so I think we can accept it, right? Give us, you know. It seems like you guys may need to, you know, mute yourself again if you didn't do so. Yeah, I'm assuming everyone is back. Yeah, yeah, I think most of you. It seems like there is one of you who didn't mute yourself. And it really gave us. Okay, pretty much everyone is mute. Okay, okay. I think we can start. We can start. Oh, I used to have a Discord link, but you know, since it's not very active, so I didn't update for a long time. So I don't know this link is my Discord or not. You guys can. I probably, you know, can share the link later. Okay. Anyway, let's start. So, let's say if it's a triprotic assay, you might get, you know, 3 pH window, 1, 2, and 3. But it's also possible for you to get only 2 pH window because the last one is gone. The last one is gone. Why the last one is gone? Because the last one, the pKa3 is too big. Basically, the Ka3 is too small. And then let's say if you use strong base to titrate water, can you get a titration curve? So we can assume water is a super weak acid, right? Obviously, you cannot get a titration curve, right? You can still get a curve, but there's no pH window, right? Because the water is too small, or you can say there's no reaction. So if an acid, its pK3 is too small, you might not get a pH window, right? Alan is asking, you know, why the largest Ka acid is to the left, right? Because it's a stronger acid. So we neutralize the stronger acid first, and then the weak acid. Make sense? You can say if HA is stronger than HB, so if the base neutralizes HB first, change into B minus, and then HA will further react with B minus to produce HB and A minus. So it's pretty much the same results is HA is neutralized first. Make sense? Okay, so this is the titration curve. The next one I want to briefly talk is, probably we can quickly have a look at the electrolysis, right? I give a few examples here. You guys can think about what will be the products on cathode and the products on anode, okay? In each case. So let's say sulfuric acid, sodium hydroxide, sodium chloride, potassium iodide, copper sulfate, and AgF silver fluoride. So I will list, you know, my answer. You can think about it. Cathode is reduction, anode is oxidation, right? So you will have H2 here, O2 here. Do you agree with me for the first case? Because, you know, the competition is in between H plus. That's it. This is the only candidates, right? There's no other stuff. And for the anode, you have 2 candidates. One is the acid hydroxide, another one is the sulfate, right? So all of the polyatomic anions are very hard to gain or lose electrons. So you don't need to care about those atomic anions. How about sodium hydroxide? Our conclusion should be the same, right? Here, the 2 candidates, one is H plus, another one is Na plus. As you know, Na plus, sodium, the element is a very strong reductants, very reactive, very easy to lose electrons, which means Na plus does not want to gain electrons at all, right? So finally, you can use standard, reduction potential to explain, right? So in the anode, there is no competition. There is only hydroxide, so no problem, right? How about this one, guys? You can think about. Cathode is still hydrogen gas, right? Anode will be chlorine because the two competitors is these two. Actually, these two have pretty much similar, losing electron ability. But, the chloride has a much higher concentration than the hydroxide, right? So according to the Nernst equation, chloride will be the first one to lose electrons, change into chlorine gas. Does this make sense to you? Mm-hmm. Okay, Ki? Mm-hmm. Make sense? I think I don't need to explain further because I minus is even easier to lose electrons than chloride, right? I minus is even easier based on the periodicity, right? Cathode have reduction, right? Anode have oxidation, yeah. So I think we can answer your question. How about this one, copper sulfate? Yes, the cathode reduction is copper and the anode is O2. Makes sense, right? How about the last one? So the cathode definitely will be Ag, right, silver, because Ag plus is very easy to gain electrons. Ag is a post-hydrogen metal, right? How about here? Yeah, here will be O2. Here will be O2. Because the two candidates, one is fluoride, one is hydroxide. So although hydroxide has a much lower concentration, but F minus is so hard to lose electrons. Because F2 is so strong to gain electrons, right? So I think it makes sense, right? Okay, I think here we summarize, pretty much all of the types of electrolysis. So basically, as you can see, the first two are electrolyzed water, right? And these few are kind of, produce, one product, another one is either hydrogen gas or water. So if there are any products, both the cations and the anions are kind of, gaining and losing electrons. Can you try to think about one example like this? I think it's not hard to find one. Let's say copper chloride. Oh yeah, like molten, sodium chloride. So you got copper here, you got chlorine gas here, you got sodium here, you got chlorine gas here. Okay, let me have a look at your question. Does hydroxide almost always behave in between F minus and? Yeah, I think it's more likely it's in between F minus and chloride. And bromine and iodide is much easier to lose electrons. Where does hydroxide from? It's from water, right? The auto ionization of water. So it will give you a very small amount of hydroxide, but it exists, right? Sodium is produced for molten sodium chloride, has no problem, right? Because the only candidates on the cathode to gain electrons is Na plus. So there's no other option, right? Yeah, molten means no water. Yeah. I think you answered the key point. Okay, so this one is done. And let me skip this one first. If we have some time, we can talk about this later, okay? The molecular orbital theory. The next one is the delocalization versus the resonance. Let me start from one example like this. So now say I have a organic compounds like this, right? Obviously, this one has a function group, which is called amide, which is this part. So now my question is, what is the hybridization of this nitrogen? sp1, sp2, sp3, or I don't know. Okay, the correct answer should be sp2. So obviously, it disobeys the Weisbach theory, the VS-EPR theory, because according to VS-EPR, it should be sp3 because there is a lone pair. So if you count the electron domains, 1, 2, 3, 4, right? So in order to minimize the repulsion between the electron domains, it should be sp3 and a tetrahedral. Actually, is a trigonal pyramid, right? But as you know, you can draw a resonance structure for this one. So now, as you can see, this nitrogen must be sp2, right? Yeah, the lone pair is resonanced, right? So we cannot say in one resonance is sp3, in another one is sp2. So the resonance actually cannot give you a perfect, explanation. So this is why we want to use the delocalization. So what is the delocalization? Because the resonance actually is the localized bond, which means the bond, the double bond, is either between the C and O or either between the C and N, right? But the delocalized bond want to say actually all of these three atoms, oxygen, carbon, and nitrogen, they all have sp2. So if I focus on the sp2, so which means all of them have a planar structure, and each of them will have an unhybridized p orbital. So now, as you can see, if you say here is a double bond, which is the pi bond, right? So you are representing the first resonance. If you say here there is a double bond, you are represent the second, resonance structure. But you may need to, change one electron to here. So this is why you have a plus on the nitrogen, you have a negative on the oxygen. But why not we say all of those 4 electrons, 1, 2, 3, 4, they are delocalized, which means they all shared in the whole structure, right? So they make a delocalized pi bond. So 4 electrons are shared by 3 atoms or 3 orbitals. So we call this kind of bond into delocalized bond, right? So this is why all of those atoms need to be sp2 hybridized. So another typical example is the benzene, right? Each carbon is sp2 hybridized. Each one will have a unhybridized p orbital. Each p orbital have one single electron. So you can say, okay, you two are good friends, you two are good friends, and then you make 3 pi bonds. But there's another way to say, okay, these two will make a double bond, these two make a double bond, these two make a double bond. So this is the localized idea. So basically, this is the 2 resonance structures. But now we can say all of the 6 p orbitals, they are perpendicular to the plane, they are parallel to each other. So they make a delocalized, pi bonds. Yeah, in organic chemistry, this is called conjugation, right? So now we don't need to care about which 2 atoms make a double bond, right? We can say all of them are delocalized. Yeah. Okay, so I kind of, call this into rehybridization, because if you do not consider the delocalization, your analysis of the hybrid might be different. So now say this exam, this one, based on VS-EPR, it should be SP3. But now, actually, is SP2, right? So you can say this is a rehybridization process. Okay, the next one I want to talk about is the isomerism in organic chemistry. So first, we need to introduce a few concepts: structural isomer and stereoisomer, right? Structural isomer means they have different, the atoms have different connection. Different connection. Stereoisomer means they have the same connection, but different, how to say that? Different arrangement in the three-dimensional world. Yeah, so this is the major difference between, the structural isomer and the stereoisomer. And then we can further divide the stereoisomer into two types. The first one is called geometric isomer. Geometric basically means cis and trans. If you read a little bit more, you can extend it to Z and E. But today, I'm not going to talk about Z and E, okay? Optical isomer, as you know, is related to the chiral atoms, which means one carbon connected to four different, groups or atoms, and which means this molecule cannot be superimposable to its mirror image. So we call this molecule is chiral, or this carbon is a chiral carbon or a chiral center. So because, the two molecule, one is the mirror image, another one, they have different, optical property, right? They can shift, the vibration direction of the single polarized light into different direction. So this is why we call it optical isomer. So I think I need to make this clear first. Enantiomers and diastereomers are mainly assessed in the USNCO national exam. So I will skip this part here. So my key point is how to count how many isomers in total. For example, let me just give you a few examples. So can you count, how many isomers does this molecule have in total, including everything? So I need to first get the answer. Secondly, you need to summarize what's your strategy. Typically, we always start from structural isomer and then think about the stereoisomer. Some of you get 4, some of you get 5, some of you are still working. So I want to tell you the first step for you to analyze the isomers is to calculate the DBE. What a DBE is called double bond equivalence. So basically, we want to calculate if you don't know how to calculate DBE, or you can say it's called the unsaturation degree or units of unsaturation, any way you like, okay? So basically, if you don't know what is DBE, do some homework later, okay? So the DBE is 1, and then we can say how many different types of function group can be there. So it can be a CC double bond, it can be a ring. So this is based on functional group isomers or functional isomer. So the first step is calculate DBE. The second step is based on the DBE to differentiate how many different function groups we can get, right? So this is why the DBE calculation is crucial. Otherwise, you may totally forget the ring structure, right? Okay, and later we can think about the skeletal, right? Isomers. We have 4 carbons. We can do it in this way. We can do it in this way. For a ring, I can do it in this way. I can do it in this way, right? So this is called skeletal, right? Make sense? And then what the last category I should think about is the location, or it's called, what that called? I think we can, positional, yeah. So where is the double bond, right? So I can put the double bond here. I can put the double bond here, right? That's it. For this one, I can only put a double bond here. There's no other option, right? And then for these 2 structure, I have no, function group to add. The ring is already the function group. So the last, I should think about the stereoisomers. So now let's have a look. Which one will have stereoisomers? Obviously this one. This one have Z and E, or cis and trans, right? Right? Do we have more? Does this one have a chiral center? Are there any chiral atom in this structure? Obviously, no. This one is not a chiral center because these 2 groups are the same, right? So how many in total? Did I include everything? So now I think the total number is 6. I hope I include everything. You're right. The number of double bonds plus the number of cycles or independent rings is called the total number of dBe, right? If a triple bond, the dB is 2. If it's a bending ring, the dB is 4. Make sense? So I think you definitely can get a few more examples from the local exam in the recent year. If there is a ring, you need to minimize, you kind of reduce 2 hydrogens to make the ring, right? So this is why there is a dBe of 1. So if you need to check the formula, pretty much is the number of carbons times 2 plus 2. Why like this? This is how many hydrogens it's supposed to have if it's full saturated. And now you minus the number of the hydrogens, and then you can see how many pair of hydrogens is lost, right? Okay, let's try one more example. So let's say you try to draw all of the isomers of this, okay? All of them, and you count how many. I will give you, let's say 1 minute. The goal of this practice is not for you to get the correct answer. It's more likely for you to practice my strategy, right? Think about dBe first, and then you think about, what are the possible function groups, and then you think about the skeleton isomer, you think about the positions of the function group, and then you further think about, are there any stereoisomers? I need to tell you, the oxygen is not counted in calculating the dBe, because oxygen, if it's single bonded, let's say the oxygen make 2 single bonds, is kind of insert either in a CC bond, which make an ether, or insert in between a CH bond, which make an alcohol, right? If the oxygen is binded with carbon by a double bond, so which means it will reduce 2 hydrogens. So the dBe will be reflected by the number of the hydrogens. Okay, some of you are very fast. So I need to count all of them, everything, including stereoisomers. Okay, give me a final answer. Okay, so my final conclusion is there are 8, isomers. So the first step is calculate DBE. As you can see, 4 carbons should have 10 hydrogens, right? If it's saturated. So which means the DBE is 0, which means there shouldn't be any double bond or any ring, right? So the only possible, functional group for one oxygen is either an alcohol or an ether. Make sense? Yeah. So for alcohol, first we think about the skeleton. So I got 2 types of skeleton, a straight line or, with branches. And then I put the function group on different, locations, right? On different positions. So I got 2 for the first one. I got another 2 for the second one. I think those 4 are easy to understand. And for the right part, I also divided them into 2 different skeletons. And then I try to insert the oxygen between the 2 carbon atoms. You can only insert the oxygen into 2 carbon atoms. You cannot do it in between the OH atom, the CH atoms, right? If you put in CH, it goes back to the alcohol. It's not an ether anymore. So basically, I can put it here. I can also put it here, right? So I got 2 different ethers. For the second one, you can put it here. There is no other options. And finally, I check, is there any structure which has stereoisomers, right? Obviously, you can see this carbon is chiral, so which means you may have an enantiomer for this one. So in total, it's 8, 7 structural isomers and 1 stereoisomers, 8 in total. Okay, limited by the time, I cannot give you more examples here. You can, practice, the strategy by, practicing the local exam, the national part 1, right? There's one more here, right? This is chiral, which means the mirror image is different. Yeah, one is R, another one is S. Make sense? Yeah, I got 5 in the left side and 3 in the right side. The 5 is 4 plus 1. This one is the stereoisomer. The 3, I think, is clear, right? Yeah, I'm pretty much done. Yeah, we use around 95 minutes. Pretty much, finish what I plan to do, except one of the contents, which is the molecular orbital theory. I hope it's helpful in some degree to some of you. Probably not, so helpful to all of you because maybe your background is different, and actually our speed is not slow at all. I cannot explain it, really clearly into a how to say that. So I hope you all pick up something from my review session today. Okay, so yeah, thanks everyone to join me tonight, and hopefully we might have opportunity to meet for another time, probably for national exam, because I don't think I'm supposing to have another review session for the local exam, since the local exam is going to be administrated starting from tomorrow, right? So a reminder for you guys, don't discuss, any question, even you finish the local exam with anyone, because, the others are still taking it. And lastly, best luck to all of you. I will try to, update my Google Classroom and the Discord server in my website, or probably I can send to you by email. If you need any more support from me, maybe we can, have a kind of, utilize the Google Classroom or the Discord, right? I will try to be online to answer your questions if I have time, okay? Okay, thank you guys. It's time to say goodbye. Good night. Hopefully we can see you next time. Best luck. Bye-bye.